Hello everyone. In our previous discussions, we explored how to find the area under a curve using technology to approximate it. Today, we're going to dive deeper and learn how to calculate these areas precisely and analytically. Our main topic is the further links between the concept of area and the mathematical tool of integrals. By the end of this lesson, you will be able to evaluate definite integrals analytically using the fundamental theorem of calculus. And you'll be able to use definite integrals to calculate the exact area between a curve and the x-axis, or between two different curves. The key to all of this is a monumental result in mathematics. It's the bridge that connects differential calculus and integral calculus. This is often called the fundamental theorem of calculus, part 2. It states that the definite integral of a function's derivative, g' of x, from a lower limit a to an upper limit b, can be found by first finding the original function g of x, and then evaluating it at the upper limit b and subtracting its value at the lower limit a. Let's break down this notation. The expression in the square brackets with the limits a and b is just a shorthand way of writing g of b minus g of a. So, to find the value of the definite integral, we find the antiderivative of the function we're integrating, and then we evaluate the difference of the antiderivative at the limits of integration. It's not at all obvious why finding an area should have anything to do with reversing differentiation. This connection was discovered independently by Isaac Newton and Gottfried Leibniz in the 17th century, and it revolutionized mathematics. So let's explore why this incredible theorem is true. In this scene, our goal is to understand the proof of the fundamental theorem of calculus. We want to prove that the area under the curve y equals f of x from a to b is indeed given by the definite integral. Let's start by proving that the area under the curve y equals f of x is the integral of f of x from a to b. Consider a general function, y equals f of x. Let's define a new function, which we'll call capital A of b, to be the area under the curve from some starting point a up to a variable endpoint b. Now what happens to this area if we increase b by a tiny amount? Let's call this tiny change delta b. When we change b by delta b, we add a small sliver of area, which we'll call delta a. Now, if delta b is very, very small, this little sliver of area is almost a perfect rectangle. The width of this rectangle is delta b, and its height is approximately f of b, the value of the function at that point. So we can say that the change in area delta a is approximately f of b times delta b. This is an approximation because the top of the sliver is curved, but as delta b gets smaller, the approximation gets better and better. If we rearrange this, we get that delta a divided by delta b is approximately f of b. This expression is the average rate of change of the area with respect to b. Now for the magic of calculus. What happens in the limit as delta b approaches 0? The expression delta a over delta b becomes the derivative of a with respect to b, or deciampere per decibel, and the approximation becomes an exact equality. So, the instantaneous rate of change of the area function is equal to the height of the original function at that point. This is a profound connection. So, if the derivative of our area function a is f, then to find the area function a itself, we must do the reverse of differentiation. We must integrate. This means the area function, a of b, is the indefinite integral of f of b, which we'll call capital F of b, plus a constant of integration, circa. Here, capital F is the antiderivative of f. We're almost there. We want the area between a and b. This is the total area up to b minus the area up to a. So the area is a of b minus a of a. Substituting our expression, we get f of b plus c minus the quantity f of a plus circa. Notice that the constants of integration, the c's, cancel out. This leaves us with f of b minus f of a, which is exactly the definition of the definite integral from a to b, and so we've proven the theorem. To recap, we've just demonstrated why finding the antiderivative of a function allows us to calculate the exact area under its curve. The key was realizing that the rate of change of the area function is the original function itself. Now that we understand the theory, let's put it into practice. Our objective in this scene is to use the fundamental theorem of calculus to evaluate a definite integral analytically. Let's work through an example. We want to evaluate the definite integral of x cubed from 1 to 2. According to the theorem, we need to follow a two-step process. First, find the antiderivative. Second, evaluate it at the limits. First, we find the indefinite integral of x cubed. Using the power rule for integration, we add 1 to the exponent and divide by the new exponent. So the integral of x cubed is x to the 4th power divided by 4. You might ask, what about the constant of integration, the plus c? As we saw in the proof, for definite integrals, it will always cancel out. So for simplicity, we can leave it out. It wouldn't be wrong to include it, but it would just cancel in the next step. Now, we write our antiderivative in the square bracket notation, with the lower limit, 1, at the bottom, and the upper limit, 2, at the top. This notation is a reminder to evaluate at these 2 points and subtract. The rule is always upper limit value minus lower limit value. So we substitute the upper limit, 2, into our expression, giving us 2 to the 4th over 4. Then we subtract the result of substituting the lower limit, 1, which is 1 to the 4th over 4. Now we just do the arithmetic. 2 to the 4th is 16, so we have 16 over 4, which is 4. And 1 to the 4th is 1, so we have 1 over 4. The final result is 4 minus 1/4, which is 15 quarters, or 3.75. So the exact area under the curve y equals x cubed, between x equals 1 and x equals 2, is 3.75. We've successfully used the theorem to find an exact value. To recap, the process is, find the antiderivative, plug in the upper limit, plug in the lower limit, and subtract. We have now successfully evaluated a definite integral analytically. While the analytical method is powerful, it has its limits. In this scene, our objective is to recognize when technology is necessary for integration and how to use it. Not every function has an antiderivative that can be expressed in terms of what we call elementary or standard functions, like polynomials, trig functions, or exponentials. A classic example is the function e to the power of negative x squared. This function is incredibly important in statistics. It's the basis of the bell curve, or normal distribution. However, its indefinite integral, its antiderivative, cannot be written down using any combination of standard functions we know. This is a fascinating point. It's not that we aren't clever enough to find it. It has been mathematically proven that no such expression exists. So how do we find the area under this curve? We must rely on technology, which uses sophisticated numerical methods to find a very accurate approximation. Using a graphing calculator, we can input the function, the variable of integration, the lower limit 0, and the upper limit 1. The calculator will perform a numerical calculation and give us an answer. The calculator might display a value like 0.74682411328. If we're asked to give the answer to 3 significant figures, we would round this to 0.747. This doesn't mean the area doesn't exist. It absolutely does. In fact, mathematicians have given a name to the function that represents this area. It's called the error function, or ERF of x, but defining a new function is different from expressing it in terms of old ones. In summary, we've learned that while the fundamental theorem of calculus provides a powerful analytical method, some important functions cannot be integrated using standard techniques. For these, we rely on technology to find accurate numerical approximations of the definite integral. Knowing when to use which tool is a key skill. We've seen that definite integrals calculate area. But what happens when the area we're interested in lies below the x-axis? Our objective here is to understand how definite integrals handle negative function values and how to find the correct geometric area. Let's investigate the area between a curve and the x-axis. Remember that the integral is essentially a sum of tiny rectangles of height f of x and width dx. If the function f of x is below the x-axis, its value is negative. So the height of our rectangles is negative. This means that if a function is entirely below the x-axis over an interval, its definite integral over that interval will be a negative number. The integral gives us a, quote, signed area. Let's see this with an example. Let's find the area enclosed by the parabola y equals 3x squared minus 4 and the x-axis between x equals minus 1 and x equals 1. First, it's always a good idea to sketch the graph. This parabola opens upwards, with its vertex at 0, minus 4. Between x equals minus 1 and x equals 1, the entire curve is below the x-axis. So, we should expect our definite integral to come out negative. Let's calculate it. We set up the integral from minus 1 to 1. The antiderivative of 3x squared is x cubed, and the antiderivative of minus 4 is minus 4x. So we have x cubed minus 4x to be evaluated from minus 1 to 1. Plugging in the upper limit gives 1 minus 4, which is minus 3. Plugging in the lower limit gives minus 1 minus minus 4, which is minus 1 plus 4, or 3. So we have minus 3 minus 3, which equals minus 6. As predicted, the integral is negative. But area, as a geometric concept, cannot be negative. So how do we find the area? To find the actual area, we take the absolute value, or modulus, of the integral's result. The area is the absolute value of minus 6, which is 6 square units. To recap this important point, a definite integral calculates signed area. If the function is below the x-axis, the integral is negative. To find the geometric area, you must take the absolute value of the result for any regions below the axis. Now we know how to handle areas below the x-axis. We've handled areas entirely above the axis and entirely below. But what if a curve crosses the x-axis within our interval? In this scene, our objective is to learn the correct method for finding the total area in such cases. Let's consider a situation where the area is partly above and partly below the x-axis. Let's find the total area between the curve y equals x squared minus 2x and the x-axis from x equals 0 to x equals 4. First, let's visualize. The graph of this parabola crosses the x-axis at x equals 0 and x equals 2. So between 0 and 2, the area is below the axis. Between 2 and 4, the area is above the axis. A common mistake is to just integrate straight from 0 to 4. Let's see why that's wrong. If we integrate from 0 to 4, the negative area from the first part will cancel out some of the positive area from the second part. The result, 16/3, is the net area, not the total physical area. To find the total area, we must treat the parts above and below the axis separately. The correct method starts by finding where the function crosses the x-axis. We already know this is at x equals 2. We must split our integral into two parts at this intercept. We'll calculate the integral from 0 to 2 and the integral from 2 to 4, and then add their absolute values. First, the integral from 0 to 2. We calculate this to be negative 4/3. So the area of this piece is the absolute value, which is positive 4/3. Next, the integral from 2 to 4. Evaluating this gives us 20/3. Since it's positive, this is the area of the second piece. Finally, we add the two positive areas together. 4/3 plus 20/3 gives us 24/3, which simplifies to 8. The total shaded area is 8 square units. This process can be summarized with a single formula, which is especially useful when using a calculator. The total area is the integral of the absolute value of the function. The absolute value function effectively flips any negative parts of the graph above the axis before the area is calculated. To recap, when a curve crosses the x-axis, you must find the intercepts, split the integral at each intercept, calculate each integral separately, take the absolute value of any negative results, and then sum them up. We have now mastered finding total area. Now let's move on to a slightly more complex scenario, finding the area trapped between two different curves. Our objective is to learn the formula for the area between two curves and understand why it works. Suppose we have two functions, f of x and g of x, and we want to find the area of the region enclosed between them from x equals a to x equals b. Let's assume for a moment that f of x is the top curve and g of x is the bottom curve. The logic is quite intuitive. The area we want is the total area under the top curve, f of x, minus the area under the bottom curve, g of x. In terms of integrals, this means we take the integral of f of x from a to b, and from that we subtract the integral of g of x from a to b. Now, we can use a property of integrals that allows us to combine two separate integrals with the same limits into a single integral. This gives us our key formula. The area between two curves is the integral of the top function minus the bottom function. The expression f of x minus g of x represents the vertical height of the region at any given x. A common question is, what if one or both of the curves dip below the x-axis? Does the formula still work? The answer is yes, it works perfectly. This subtraction, f of x minus g of x, always gives the positive vertical distance between the curves, as long as f of x is above g of x. The formula is independent of the x-axis. So, the general strategy will be, first, find where the curves intersect to determine the limits a and b. Second, determine which function is on top in that interval. And third, set up and evaluate the integral of "top minus bottom." To summarize, we've derived a powerful and general formula for finding the area between any two curves. The area is the integral of the difference between the upper and lower functions. Let's apply our new formula for the area between curves to a concrete example. Our objective is to follow the complete process to find the area enclosed by two parabolas. We need to find the area enclosed by the curves y equals 7x minus x squared and y equals x squared minus 3x. The first step is always to find the limits of integration. Since they aren't given, they must be the points where the curves intersect. To find the intersection points, we set the two functions equal to each other. Now we solve for x. Let's move all terms to one side. We get 2x squared minus 10x equals 0. Factoring out 2x gives 2x times the quantity x minus 5 equals 0. This gives us two solutions, x equals 0 and x equals 5. These are our limits of integration, a and b. The second step is to determine which function is on top and which is on the bottom in the interval from 0 to 5. We can do this by picking any test point between 0 and 5, for example, x equals 1. For the first curve, y is 7 minus 1, which is 6. For the second curve, y is 1 minus 3, which is minus 2. Since 6 is greater than minus 2, the curve y equals 7x minus x squared is the top function. Now we have everything we need to set up our integral. The area is the integral from 0 to 5 of the top function minus the bottom function. Be careful with the parentheses to ensure you subtract the entire second function. Let's simplify the expression inside the integral. 7x minus negative 3x is 10x. And negative x squared minus x squared is negative 2x squared. So we need to integrate 10x minus 2x squared. Now we find the antiderivative. The integral of 10x is 5x squared, and the integral of 2x squared is 2/3 times x cubed. Finally, we evaluate at the limits. Plugging in 5 gives 125 minus 250 over 3. Plugging in 0 gives 0. Finding a common denominator, we get 375 over 3 minus 250 over 3, which equals 125 over 3. The exact area enclosed by the two parabolas is 125 over 3. We have successfully followed the entire procedure. Find intersections, identify the top curve, set up the integral of the difference, and evaluate. To become truly proficient with integration, it's helpful to know some of its fundamental properties. In this final scene, our objective is to review these key properties and use them to solve some more abstract problems. Let's look at some essential properties of definite integrals. First, if you swap the limits of integration, the value of the integral is negated. This makes sense because f of b minus f of a is the negative of f of a minus f of b. Second, an integral from a to c can be split at any point b in between. The area from a to c is the area from a to b plus the area from b to c. We use this idea when dealing with curves crossing the x-axis. Third, a constant multiplier can be pulled outside the integral. Integrating 3 times a function gives the same result as finding the integral of the function and then multiplying by 3. Let's use these properties to solve a problem where we don't even know what the function is. Suppose we are given that the integral of some function f of x from 2 to 5 is 10. We need to find the integral of 3 times f of x minus 1 over the same interval. First, we can split the integral of the difference into the difference of the integrals. Next, we use the constant multiple rule to pull the 3 outside the first integral. Now we can substitute the given value. We know the integral of f of x is 10. For the second part, the integral of 1 is just x. So we have 3 times 10, which is 30, minus the value of x evaluated from 2 to 5, which is 5 minus 2, or 3. The final answer is 30 minus 3, which is 27. Let's do one more type of problem, where we have to solve for an unknown limit of integration. We need to find the value of a that makes the integral of 3 over the square root of x from 1 to a equal to 24. First, let's evaluate the integral. We rewrite the integrand as 3 times x to the power of negative 1/2. Using the power rule, we get 6 times the square root of x. Now we apply the limits. This gives us 6 times the square root of a minus 6 times the square root of 1. We set this expression equal to 24. Now we just solve the equation for a. Adding 6 to both sides gives 6 root a equals 30. Dividing by 6 gives root a equals 5. Squaring both sides, we find that a must be 25. Today, we have journeyed from the theoretical proof of the fundamental theorem of calculus to its practical application in finding areas. We've learned to handle areas above, below, and between curves, and we've explored the properties that make definite integrals such a flexible tool. This connection between area and the antiderivative is a cornerstone of calculus. Well done, everyone.